Okay, now we're going to talk about some theorems for line integrals. And let's just start by remembering the fundamental theorem of calculus. If f prime is continuous on an interval a, b, then we can say that the integral from a to b of f prime of x dx is f of b minus f of a. So there's a theorem for line integrals that kind of follows this. I'll just call it a line integral theorem. Okay, let r of t be the position vector, so it's going to represent a smooth curve on an interval AB. F is a function that's differentiable, and the gradient of f, or del f, is continuous on the curve. Then we can say the line integral gradient f dotted with dr is f of r of b minus f of r of a. So it looks like the fundamental theorem of calculus, actually. So if C is a curve with terminal point B and initial point A, then that's equal to f of B minus f of A. Okay, let's do some definitions. I'm not going to prove these. All the proofs are in your text. I want you to look at those proofs in your text. Let's say definition of a path. A piecewise smooth curve connecting points A and B is called a path. Here's another one. A line integral is said to be independent of path if no matter what path we follow, we get the same result. The value of the integral only depends on the endpoints. So here's A and here's B. It doesn't matter how I get there. Could be that path, could be that path. Any way you do it, or if you integrate along any curve, you're still going to get the same answer going from A to B. Okay, this brings us to another theorem. F is a vector valued function continuous on D, then the line integral is independent of path if and only if f is conservative. Remember, that means f is equal to the gradient of some function f. Okay. So you can use that theorem. Again, the proof is in the book. Also, let's go through some definition. Curves are closed if the endpoints are equal to each other. If where it starts is where it ends. So this is a closed. These are closed curves. Curves are simple if they do not intersect themselves. So the first one above is simple, the second one is not simple. Okay, so simply connected region means that every simple closed curve in the region contains points that are only in D. So again, this is simply connected. Something like this that has a hole in it is not simply connected. Because in the center, those aren't in the region. Those points aren't in the region. Okay, so all this is really important for the next theorem, actually the last theorem that we're going to talk about. Okay, there has to be a lot of conditions here. So let f is the vector valued function. And D is simply connected. P and Q have continuous first partial derivatives. Partial of P with respect to Y is equal to the partial of Q with respect to Y in the region. If all those conditions hold, then F is conservative. Okay, so, and this has a lot of applications in the sciences. And you can look at, we're not going to do applications here, but you can look in the book for some of the applications of this.